All right, everybody, welcome to the first video control systems lecture. So when we last left our discussion, we were talking about analyzing the response of systems using this concept of natural frequency and damping ratio. And the idea there was we can consider the form of the response of a system without necessarily caring directly about what frequency it's operating at. So is the system operating in the gigahertz range, or the hertz range, or the megahertz range, or the millihertz range? Well, they're going to have a similar response regardless of what scale that frequency is. So maybe for the purposes of doing the analysis, let's just strip away the information about what particular frequency we're operating at and just look at sort of the general shape of the response, the form of the response. So that created this zeta term, which is our damping ratio, and the natural frequency term. And where we left off last time is we said we can look at the second order polynomial in a transfer function and we can directly pull out these terms. It's really handy. We can just look, by just looking at that polynomial in the denominator of our transfer function, we can see what the damping ratio is going to be, what the natural frequency is going to be, and so on. So what I want to do right now is write, we sort of showed last time sort of how to pull out those components. But now I'm going to write sort of the generic form of a second order transfer function with these terms included. So transfer function okay. So one thing to note. No coefficient in front of the highest order S term here. So no coefficient in front of the S squared term is very important for doing this analysis. So none of this works if you have some term here. What you have to do is you have to massage your transfer function into this form. Once it is in this form, you can pull out the natural frequency, you can pull out zeta, and you can identify sort of the type of response that this is and the nature of this response. Okay. So let's do an example. Okay. So please find the damping coefficient and the natural frequency of this system. Pause the video, find this on your own. Should be pretty easy. All right, welcome back. So the first thing we're going to do is we're going to find the natural frequency here. So this term is the natural frequency squared. So the natural frequency is going to be the square root of 36, which is 6. Next thing we know is we know that 4.2 is going to be 2 zeta omega n, so this is going to be, so we can say 4.2 equals 2 4.2 equals 2 times 6 times zeta. So zeta equals 4.2 divided by 2 times 6. That equals 0.35. We did it. Very easy to do. So again, when we've analyzed systems in the past, it's a process of identify, is it overdamped, underdamped, critically damped. Based on those two, find the form of the equation. Based on the form of the equation, solve for the coefficients and all sorts of stuff like that. We're actually kind of bypassing that in this case. In this case, we're directly solving for these features of the shape of the response of the system from the transfer function. It makes it much easier for us to actually very quickly see how a system is behaving. Okay, let's go back to our 4 forms of our response. We have overdamped, critically damped, underdamped, undamped. Let's look at how changes in the damping coefficient vary between those 4 phases. So let's do our zeta poles step response. Okay. So when zeta is 0, when the damping coefficient is 0, the poles of our system are going to be on the imaginary axis, and they're going to have a location of j omega n, where omega n is the natural frequency. This is the undamped response. So you know that. We have poles on the imaginary axis. Those are going to be undamped sinusoids. Those are going to be sinusoids that are not bounded by a decaying exponential. They're also not bounded by an increasing exponential. But so we just get this, undamped response here. What about when we have a damping ratio that is in between 0 and 1? So a damping ratio in between 0 and 1 is, and you can imagine as we start to add damping to the undamped response, we are going to start to get an underdamped response to this system. So in the case of the, and I'm going to space this out a little bit, sorry. In the case of the undamped or underdamped response, we're going to have complex poles. The imaginary component of those complex poles is going to be j omega n square root of 1 minus the damping ratio squared. The real component of those is going to be negative damping ratio times the natural frequency. This response is going to be a decaying, it's going to be a sinusoid bounded by a decaying exponential. What about when our damping coefficient is equal to 1? Damping coefficient is equal to 1 is the case of repeated roots, and the location of those repeated roots is going to be negative the damping ratio times omega n. And this is the critically damped response. And what about for our damping ratio greater than 1? So, damping ratio greater than 1, there's only one left. We're going to have real and distinct roots. The position of those roots is going to be negative zeta omega n plus or minus square root of zeta, oh boy, zeta squared minus 1. If you can't see this well in the video, you can follow along in the book. They go through the same thing. This is going to be the overdamped response. So this is a really handy tool. You can see how powerful this is. We can look at the form of the transfer function. We can identify the natural frequency and the damping ratio. We can immediately say which type of system this is. And we can immediately say what the location of the poles are. And again, we can find these equations just by doing, the quadratic equation on this guy over here. I mean, all of these can be found using the quadratic equation. It's not, these aren't, I didn't derive them all, but it's not voodoo to find them. You can do it on your own. But looking at these 4 types of system responses, which type of system response do you think is the most special? Which system response do you think is the one that we're probably going to pay the most attention to in terms of fine-tuning exactly how the system is responding? Well, all of these are relatively boring except for in here. So in here where we have the Underdamped response, this is really where most of our attention is going to lie in sort of really specifying what's going on with the response of this system. Many systems have at least a component of their response which is an undamped response. Sometimes that undamped response is small compared to the other response of the system, compared to other poles in the system. But typically this is the one where we sort of have the most concern about exactly where is this pole. And keep in mind again, as the pole moves closer here, we get closer and closer to the undamped response. As the pole gets closer to here, we get closer and closer to the critically damped response. But there's a lot of detail in exactly where this pole is in this quadrant that tells us a lot about how our system responds to things. Okay, let's do a quick example problem though. So we have a system with some input. It's got our transfer function 12 over s squared plus 8s plus 12. And then it's got some output c of s. So our question now is, for this system, assuming we have a step response, or step input, what does the response of this system look like? So find for this system, find the natural frequency, find the damping ratio, and then determine based on that what type of system response this is. Is it undamped, underdamped, critically damped, overdamped? Okay, I'm going to pause the video, do it on your own, then we'll come back. Welcome back, everybody. So again, pretty easy. Natural frequency is going to be the square root of 12 here. And our damping coefficient is going to be 8 divided by 2 divided by square root of 12. 1.155. So our damping coefficient was 1.155. What type of system response is that? That is the overdamped response, yes. So see, it's very powerful to use these tools. We can very quickly go from a second order system to identifying how that system is going to respond. So, just like in the case of the first order system, in the first order system we said, what are our metrics for determining system response? Time constant, tau, rise time, settling time. Right? These are sort of our parameters for it. What about in the case, those are still the parameters that we would use for, say, like an overdamped system. We can still use that. We can still use some of those for the other phases. But obviously, if we had an undamped system, settling time doesn't make any sense for that. If we had an undamped system, rise time and fall time doesn't really make a whole lot of sense. Or even if we have an underdamped system, some of those terms might not make any sense. So what we're going to do now is we're going to look at what are the ways that we characterize the response of an underdamped system, and specifically, what are the parameters we use to make decisions about whether or not our system will meet our needs of our control system. So again, some control systems, depending on the needs of the person using the system, might be more okay with one attribute or another. Based on our specifications, we need to evaluate the response and see if that particular response meets those needs. We're going to look at those common metrics that we're going to use. For an underdamped system, we still care about rise time. Right. So an underdamped system, we are still going to rise in an underdamped system, we are just going to rise, but then we're going to overshoot our goal, right? So an underdamped system, remember, the response is going to look something like that, right? So we are still going to have that 10 to 90% rise time here. So we still have rise time. And again, rise time is that 0.1 to 0.9 rise. We have time to peak. So the time to peak is the time it takes for us to hit our first maximum peak. So that would be here to here, right? Time to peak. So percent overshoot. Percent overshoot is an important one. Percent overshoot would be the magnitude of this overshoot here relative to the magnitude of our step change. So it's saying if we're making a step of, if we have a system that is, controlling a voltage and we have a step of 10 volts, it's saying, and we overshoot by 1 volt, that would be a 10% overshoot of our system. So that's how far, when we overshoot our mark, which we always do in the case of an underdamped system, the question is how much do we overshoot it by? So that is percent overshoot. And then we also have settling time, which is again, so settling time, again, remember, these systems are bounded, an underdamped system is still bounded by a decaying exponential. And that decaying exponential still tells us how long it'll take to guarantee that we're not going to exceed sort of a 2% error from our final value. So we can still look at things like settling time for the case of the underdamped system. Okay. So there's some handy ways that we can find some of these features. So the book gives a lot of handy tools for you. There's a lot of tables that you can use to find some of these, equations that you can use. Not all of the parameters we're looking at can be found explicitly. Some of them you have to use a table to find. Or some of them will use an approximation, an approximate solution. So let's look for these 4 parameters. Time to peak. Time to peak would be pi over the natural frequency times the square root of 1 minus damping ratio squared. Percent overshoot. It's going to be e to the negative damping ratio pi over square root of 1 minus damping ratio squared. Times 100. It is a percent after all. Now, what does this look like? If we look at percent overshoot versus damping ratio, as the damping ratio goes from 0 to 1, the percent overshoot goes from 100 to 0. 100% overshoot? The damping ratio of 0? Yeah, an undamped system is literally going to have a sinusoid that fully overshoots the system and fully goes back to our original position before we made the step. Percent overshoot of 0? Yeah, that's what we get. That is critically damped system is right at that threshold where the percent overshoot becomes 0. And this is sort of the curve that we get from that. And again, this is just defined by this expression. Now, what's our settling time? Settling time is negative natural log of 0.02 square root of 1 minus damping ratio squared divided by damping ratio times the natural frequency. And if we don't like that, and we don't like that, If we don't like that, we can use an approximation to say settling time is about equal to 4 over the damping ratio times the natural frequency. So why do we have natural frequency in these three things? TP, TS, just TP and TS. TP and TS both have natural frequency components. Why? We said the shape of the system can be defined fully by the damping ratio. But in this case, we were trying to find a time. Once we're finding a time, we can no longer look at just the shape of the system. We have to look at the shape of the system, and we have to look at that overall time constant. So we have to incorporate this natural frequency back in these expressions if we're trying to pull an actual time out. Because if our system is operating at gigahertz scale, or if it's operating at the millihertz scale, absolutely, that natural frequency scale is going to matter, not just the shape of the system response. Why does a percent overshoot not have a natural frequency term? How come this is the one component that doesn't have that? Talk amongst yourselves. Pause the video. Welcome back. What'd you find? Percent overshoot. Why does it not care? Percent overshoot is not a function of the scale, the frequency scale of the system. It is, again, it is a ratio. It is an overshoot ratio. It is purely a function of the shape of the underdamped response. So it doesn't matter if it overshoots in a millisecond or it overshoots in a nanosecond. It's the percent that it overshoots, not the time that it takes to overshoot or anything like that. Okay. I'm going to take a little break. You take a break, take a stretch, do some torso stretches, get moving, and we'll come back.